Okay, and to finish off the Surds section of our Surds and Indices topic, we want to finish off looking at rationalising the denominator. So, as I mentioned in the previous video, we want to look at when we have more complex denominators. So you'll see in all these examples, the denominators have two terms to them. So in the previous example, let me just start with this. If this example had been 5 on root 2, don't write this down, just concentrate. We know that we multiplied the top and the bottom by root 2 because root 2 times root 2 makes that rational, and we get 5 root 2 on 2. Okay? Now, nice rational denominator. If, however, we have 5 over 3 minus root 2, if we were to multiply the top and the bottom here by root 2, we would get 5 root 2 on the numerator, and then it's root 2 times 3 minus root 2. 3 minus root 2. And when we expand out that bracket on the denominator, it's root 2 times 3, which is 3 root 2, minus root 2 times root 2, which is 2, which is great. That's rational. But actually, the denominator isn't rational because we've got this surd still here. So multiplying 3 minus root 2 by root 2 doesn't make it rational. So the question is, okay, well, how do we make such an expression rational? And we've actually done this in a couple of videos ago. If we think about expanding and simplifying this is our difference of two squares, a minus b times a plus b. And the reason that's so helpful when we have surds in these brackets is because when we expand out a minus b times a plus b, we get a squared minus b squared. And squaring surds is a great way to make them rational. So in this case, this would be 3 squared minus root 2 squared, which is 9 minus 2, so 7, which is rational. And so we multiply 3 minus root 2. We don't multiply it by itself, we multiply it by 3 plus root 2, so that we create this difference of two squares. It's all about the difference of two squares, rationalising these complicated denominators. So if it was 3 plus root 2 on the denominator, we would want to multiply the top and the bottom by 3 minus root 2. If it's 3 minus root 2 on the denominator, we want to multiply the top and the bottom by 3 plus root 2. And by doing that, we create this difference of two squares pattern on the denominator, which we know when we expand that out is going to give us something rational. Okay? So we call these conjugate pairs. 3 plus root 2 and 3 minus root 2 are conjugate pairs. 3 minus root 2 is the conjugate of 3 plus root 2 and vice versa. And so we need to use these conjugates to rationalise denominators with two terms. So it's not just about multiplying by root 2, it's also not just about multiplying by itself. We don't want to multiply by 3 minus root 2. Okay? If you did, that's a really common error. Students go, oh, I multiply it by itself, but 3 minus root 2 times 3 minus root 2, well, that's 3 minus root 2 squared, which is 3 squared minus 2 times 3 times root 2 plus root 2 squared. That's a perfect square, which is 9 minus 6 root 2 plus 2, which is 11 minus 6 root 2, which is not rational. Okay? So it doesn't help to multiply by itself. You must multiply by the conjugate pair. So the same terms, but with, if it had a minus if there was a minus in the original term, then you'll have a plus. If there's a plus, you'll then have a minus. So in this case, we're going to have 3 minus root 2 times 3 plus root 2 on that denominator. And so we need to multiply the top and the bottom by the same thing. So again, remember, in terms of what you say, we're not multiplying by 3 plus root 2, we are multiplying by 1. 3 plus root 2 on 3 plus root 2 is 1. Anything divided by itself is 1. So we're just multiplying by 1, which is why it's allowed. But we're going to create this conjugate pair, which is going to allow us to rationalise the denominator. So on the numerator, we're going to have 5 times 3 plus root 2. You can expand that out straight away if you want to. On the denominator, we've now created this difference of two squares, and so we're going to have 3 squared minus root 2 squared. So expanding out the numerator, we've got 15 plus 5 root 2, and on the denominator, we've got 9 minus 2, which is 7. So we've got 15 plus 5 root 2 over 7. No common factors between the numerator and denominator. There is a common factor of 5 on the numerator, but 5 doesn't cancel down with the 7, so there's no need to factor it out. Okay, example 2. So our current denominator is 1 plus root 3, so I'm going to need to multiply by its conjugate pair, which is 1 minus root 3, so that I create this difference of 2 squares on the denominator. Okay, so we must multiply the numerator by the same thing, and again, we're not multiplying by 1 minus root 3, we're multiplying by 1 by doing that. As long as we multiply the top and the bottom by the same thing, we're just really multiplying by 1. So the numerator is 7 times 1 minus root 3. The denominator, we've created this difference of 2 squares by multiplying by the conjugate, and so it's going to be 1 squared minus root 3 squared. So numerator, expanding that out, 7 minus root 3, 7 minus 7 root 3. Denominator is 1 minus 3. And so it is 7 minus 7 root 3 all over negative 2. Now, there's nothing wrong with that technically. The answer is correct, but this negative in the denominator is a bit ugly. So if I multiply both the numerator and denominator by negative 1, I now get positive 7 root 3, negative 7, and positive 2. Okay, so this would be a nicer way to write the answer. So all we did there was multiply by negative 1 over negative 1, which is 1. We did the same to the top and the bottom. Okay, example 3. So the denominator is root 2 plus 3, so we're going to need to multiply by its conjugate pair, which is root 2 minus 3. So we've created that difference of 2 squares. We do the same to the numerator, top and the bottom by the same thing. So hence we're only multiplying by 1. So the numerator is root 2 times root 2 minus 3. The denominator, we've got this nice difference of 2 squares pattern, so it's root 2 squared minus 3 squared. And so numerator, root 2 times root 2 is 2, minus 3 times root 2, which is 3 root 2, all over root 2 squared is 2, minus 3 squared is 9. Okay, so on the numerator we've got 2 minus 3 root 2. On the denominator we've got negative 7. Again, we've got that negative on the denominator. Let's multiply everything by negative 1. We're multiplying top and bottom by negative 1 here, which means instead of having negative 3 root 2, we've now got positive 3 root 2. Instead of having positive 2, we've now got negative 2. And instead of having negative 7, we've now got positive 7. So this would be a nicer way. It's a bit like, it's sort of like there's a common factor of negative 1 that should be simplified. It's a bit like, you know, this answer at this line is a bit like you wouldn't leave your answer as negative 4 on negative 7. It's 4/7, okay? So if you've got that negative in the denominator, let's just multiply everything by negative 1 to get rid of it. Okay, question 4. Our denominator is root 7 minus root 2. Now this conjugate pair works if they're both surds as well. So multiplying by root 7 plus root 2, so same terms but with the opposite sign in between them. So we're going to do the same to the numerator, root 7 plus root 2. Okay, so the numerator is root 3 times root 7 plus root 2. And the denominator is, we've created that difference of 2 squares pattern, so it's going to be root 7 squared minus root 2 squared. Okay, expanding out the numerator, root 3 times root 7 is root 21. Root 3 times root 2 is root 6. All over, root 7 squared is 7, minus root 2 squared, which is 2. So 7 minus 2, which is 5. Root 21 plus root 6 all over 5. Now just checking our surds are in simplest form. There's no square numbers that go into 21. There's no square numbers that go into 6. So both of those surds are in simplest form. They're not like surds, so they can't be added together. And the fraction, there's no numbers out the front here that could be cancelled down, potentially cancelled down with the 5. So the fraction is also in simplest form. We've got a positive denominator, so everything's all good. Okay, a couple more examples. Example 5. Again, focusing on what do we need to do to rationalise the denominator. So the conjugate pair of root 10 plus 4 is root 10 minus 4. So we're going to multiply top and the bottom by root 10 minus 4. So on the numerator, we've got root 10 minus 7 times root 10 minus 4, and on the denominator we've got root 10 squared minus 4 squared from that difference of two squares pattern. Okay, we want to expand out the numerator. Root 10 times root 10 is 10. Root 10 times negative 4 is minus 4 root 10. Negative 7 times root 10 is negative 7 root 10. Negative 7 times negative 4 is positive 28. The denominator, root 10 squared is 10, minus 4 squared is 16. Okay, collecting like terms on the numerator, 10 plus 28 is 38, minus 4 root 10 minus 7 root 10 is minus 11 root 10, and the denominator is 10 minus 16, which is negative 6. Again, we've got that negative denominator. Let's multiply everything by negative 1 to get rid of that. So we're going to have positive 11 root 10 minus 38 on the numerator over positive 6. Okay, example 6. Again, we've got two surds here. Conjugate pair. We need the same terms, so 2 root 3 plus root 2. Now I know when we just had a single term, we ignored the 2. We can't do that in this case because we need to create that difference of two squares pattern. So if we were to just multiply by root 3 plus 2, we haven't got that difference of two squares pattern. So we must have the same two terms with a plus in one bracket and a minus in the other bracket. So we're multiplying top and bottom by 2 root 3 plus root 2. So sometimes you're just going to have a lot of surds. Try not to skip too many steps. You'll make mistakes. Just be careful. One thing at a time. Your denominator, you've created that difference of two squares, so it's 2 root 3 all squared minus root 2 all squared. Okay, let's expand out the numerator. 4 root 2 times 2 root 3 is 8 root 6 plus 4 root 2 times root 2. Root 2 times root 2 is 2, so it's 4 times 2, which is 8. Might write that out, but you can go straight to that if you need. 2 root 3 all squared. 2 squared is 4 times root 3 squared, which is 3, and then root 2 squared is 2. Alright, so we've got 8 root 6 plus 8 all over 12 minus 2. So we've got 8 root 6 plus 8 over 10. Okay. There is a nice common factor of 2 in the numerator and denominator, so we could just factor out the 2. There is actually a common factor of 8 in the numerator. It's root 6 plus 1. But 8's not common to the denominator, so the only thing common between 8 and 10 is 2. Okay. So your answer could be written as, 4 times root 6 plus 1 over 5, or you could have you didn't need to completely factor out the 8, so it might be 4 root 6 plus 4 all over 5. Either of these is perfectly fine. But you do need to, this is not okay here, there's a common factor of 2 that needs to be cancelled down. So dividing the numerator by 2 gets you to 4 root 6 plus 4, and dividing the denominator by 2 gets you to 5. Okay, final example. I know we've done quite a few here, and we've got a lot of surds going on here. We want to add together two fractions, so we're going to need a common denominator. I don't fancy finding a lowest common denominator with these, so let's focus on instead rationalizing the two fractions first, and then we can focus on the fractions. So, first one is root 5 plus root 2. We need to multiply it by root 5 minus root 2 to rationalize that denominator. Okay, and then the other term is 3 root 2 over 2 root 3 minus root 6. So I'm going to need to multiply the denominator by 2 root 3 plus root 6, and we'll do the same to the numerator. So lots going on here, but give yourself space, write it out. You know, we're probably starting to get to a point in your maths work where, you know, ruling a column down the middle of your page might not always be beneficial because you might well be dealing with calculations that spread across the whole page. So don't be afraid to do that. You know, it doesn't matter if you have to draw through your ruled line on your page. Give yourself space, write it out properly, take your time, focus on each fraction individually, and then we'll worry about combining the fractions together. So we've got our conjugate pair here, so we've created that difference of two squares along the denominator there. The numerator is just one lot of root 5 minus root 2, so that's just root 5 minus root 2. And the denominator, that difference of 2 squares, it's root 5 squared minus root 2 squared. Okay, we'll come back to the second fraction in a minute. So we've got root 5 minus root 2 on the numerator. This is 5 minus 2 on the denominator. So it's root 5 minus root 2 over 3. Okay, let's have a look at our second fraction over here on the right. So again, we've created that difference of 2 squares along the denominator there. Okay, so numerator is 3 root 2 times 2 root 3 plus root 6 all over denominator. We've got that difference of 2 squares, 2 root 3 squared minus root 6 squared. Okay, expanding out the numerator, 3 root 2 times 2 root 3 is 6 root 6 minus, we're going to have 3 root 12 over, now 2 root 3 all squared is 4 times 3, so that's 12. Root 6 all squared is 6. Okay, other thing I'm noticing here is this. It's not in simplest form, so let's deal with that as well. So we've got 6 root 6 minus 3 times. Now 12 is 4 times 3, which means that simplifies to 2 root 3. Okay. So hopefully getting a bit more efficient at those simplifications. So in my head there, I did root 12 is root 4 times 3, which is root 4 times root 3, so 2 root 3. Okay. 12 minus 6 is 6 on the denominator. Okay, we're getting there. Let's see where we're at. 5 minus root 2 on, root 5 minus root 2 on 3, plus 6 root 6 minus, now that's 6 root 3, all over 6. Now, before we focus on common denominator here, this fraction has a nice common factor of 6, but actually, now what we could do is we could divide everything by 6. We could do this in a number of different ways, but we want to try and be as efficient as we can. So what we could recognise is everything's got a common factor of 6 there, so that's actually just root 6 minus root 3 over 1, but we don't have to write that. But then that's not helpful with adding together with here, because we actually want a common denominator of 3. So actually, rather than dividing the numerator and the denominator by 6, what I might do is just divide it by 2 so that I get a denominator of 3. So if I take 2 out of that, that's 3 root 6 minus 3 root 3 all over 6. And now that lets me cancel that down. And we're not writing that second fraction in simplest form. But what I'm doing is I'm getting the common denominator. So that I can now we've got this nice common denominator here. And so we can add these together. So we've now got all of that over 3. We've got root 5 minus root 2 plus 3 root 6 minus 3 root 3. Any like terms? Nope, no like terms there, so we're all done. Let's just be cautious about one other common error. If this had been an extra step of, if this had instead been a minus, you would need to be really careful about the fact that you are subtracting all of that second numerator. And so actually when you do that, it will be minus 3 root 6 and plus 3 root 3. So that wasn't the question, but again, just harking back to some of that fraction work we did back in chapter 1 and making sure that we're really careful when we're subtracting big ugly fractions like these. Okay, so our answer didn't simplify very neatly, but we have ended up with something with a rational denominator. Yes, we've got 4 unlike surds on the numerator, which we can't do anything about. Okay, so worksheet, rationalising the denominator part 2. So with these more complex binomial denominators, so that is denominators with 2 terms, and the important thing is to use this difference of 2 squares, the conjugate pair, to rationalise the denominator.